Dysfunctional Vet here. I'm about to begin an explanation of celestial navigation. I am not going to teach a course on celestial navigation because A, most people would find it too boring, B, it would take way too long, and C, this course is best taught with a book, a sextant, a chart, a sky with a sun, a moon, planets, and stars. It's best taught hands-on. So I would recommend a copy of Dutton's Navigation as a real good book. There's another one which I dug up. This is the Down and Dirty. It's the last name is spelled I believe DeGraff. Okay, the book itself is by Mary. The last name is B-L-E-W-I-T-T. Celestial Navigation for Yachtsmen. This is a down and dirty, just the basics. But if you really want to seriously be a navigator and understand navigation, you need to get a copy of Bowditch. It's a 2-volume set. I should check on Amazon to find out what it costs. I'm figuring it's pretty expensive. I don't remember what I paid for it, but when I was learning navigation, I got the book on navigation, which is Bowditch. So, without further ado, let's look at what we have here. In order to understand celestial navigation, let's start with piloting. This is you right here, and you are in Crystal Baffin Bay, which is a fantastic place to go fish if you want to go there. I always loved the spelling of this because it was like castle, only it's not castle, it's crystal. Crystal Baffin Bay. It's not a real big place. You have a light buoy out here, and it's primarily so that people don't come sailing into here. You have a bell buoy right over here, which is adjacent to some rocks. You have a tower. It's an FM transmitter, and it transmits some of the funkiest music you're ever going to hear. Yeah, I think it's a private station, and the guy looks for weird stuff to transmit. You have the lighthouse here, and the lighthouse is actually not a lighthouse. It's a very tall building, Victorian style house, and in one of the top windows up there somebody put a rotating white light, and they call it the lighthouse. And now it's an aid to navigation. It's actually on the chart. That's why I put it on here. You also have the Capitol Bank building. Capitol Bank building is about, I think it's 6 stories high, so about 60 feet. When you're in this bay, you can see the Capitol Bank, the lighthouse. Day or night you can see it unless it's foggy, and you can always see the tower. This lighted buoy is real easy to see at night. It's not so easy to see during the day because of the glare off of the water. But this is you right here. This is you right here. And you want to go fish right up here somewhere. And you want to know where you are so that you can get a compass bearing. Now in a bay this small you wouldn't be doing this, but it was the easiest thing to draw on a scale to help you to understand celestial navigation. So you're here and you want to go here. You take your handheld compass and you find that the light is 45 degrees. The tower is 150 degrees. Correction, it's 15 degrees. The lighthouse is 358 degrees, and to the Capitol Bank is 278 degrees, like this. When you are doing piloting and celestial navigation, if your bearings are less than 180, you add 180 to get your back azimuth. If they're greater than 180, you subtract 180 to get your back azimuth. So 45 becomes 225, 15 becomes 195, and so forth. You would slap your protractor down on top of this with it being oriented the 0 degree to north, and you would find 225, and you draw your line right across here like this. And let's say that we use the lighthouse, which is 358. So we slap the protractor up here and we get 178. We draw our line down like this. And let's say that we use Capital Bank. We slap our protractor down and we take 98 degrees and we come back here like this. Where these three lines converge, that is where you are. Then you would use your chart and you would find where you wanted to go, and you would then sail that magnetic compass heading to that location, drop your anchor and do your fishing. When we're doing celestial navigation, we're using the sun, the moon, planets, stars. We're using these things. Let me show you that real quick. This is the Earth, North Pole, South Pole, Tropic of Cancer to the north, Tropic of Capricorn to the south, equator, equal distance here. The sun travels 1 degree every 4 days as it rises towards Cancer or as it drops down to Capricorn. And of course, when it's up here and it reaches its zenith point on the globe, as it were, you have your longest day, and when it drops back down here you have the short day. Everybody knows that. Nothing, no rocket science here. But this is your upper limit of the sun, and this is your lower limit of the sun as it travels back and forth. The stars and the moon, and I didn't draw planets in because I didn't want to make this real terribly confusing. But all of these objects here have an imaginary line that goes from the center of the Earth, which is this dot, goes through the center of the moon, comes out to the stars, goes up to the sun, and also to the planets. This imaginary line slowly moves across the surface of the Earth. Think of a string that runs through the center of the moon to the center of the Earth. And as the Earth spins, that string moves across the surface. It has a longitude and a latitude, which can be determined and can be found. The sun and the moon are calculated for every 10 minutes of time as the Earth is turning. The stars and the planets are calculated for every hour of travel. So if you're going to be doing a star sight, there's a little bit more math involved to determine where it's located. But generally speaking, the sun and the moon can quickly be calculated because it's tabulated for every 10 minutes. The sun and the moon are also frequently done, and we'll get into that in just a minute. Meanwhile, what you need to understand, and you need to commit this to memory, all points in the heaven which are used for navigation are calculated for a longitude and latitude on Earth. So this imaginary string from the center to the star, from the center to the sun, and so forth, is a known location which can be used to do your navigation. Now, one of the problems with early navigation, before we had accurate watches or chronometers, was the fact that you have to know the time in order to know where these things are positioned. The first attempts at charting these astronomical bodies in the sky was in about the 1700s. By the 1900s, even though they didn't have reliable chronometers and they would use hourglasses, they actually had somebody whose sole purpose on board that ship was to turn the hourglass so you could calculate time. Even though they didn't have accurate chronometers, they were beginning to be very, very accurate as far as where the stars and the sun and the moon and all that stuff were on the planet. So with the rudimentary chronometers they had, we're talking hourglasses here, they could navigate relatively well to wherever they needed to be. There's also some other aspects of this that I don't want to get into too much, but when you're sailing, they used to have a stick or a piece of wood, and they would cut little bitty notches on it, and they would put the string in their mouth, and they would hold it out at arm's length, and they would measure the distance above the horizon to a star, and that's how they would determine their latitude. So what you would do is you'd sail sort of in a north-south direction until you reached the latitude you wanted, and then you would turn toward shore, and that's how you would get there. There's a whole lot of very interesting things that people did to navigate, and I don't want to get into all of it, but remember, all of these things, the stars, the sun, the moon, the planets, they all have a longitude and latitude that can be determined. If you remember in the charting, we said if we know where the lighthouse is, and the radio tower, and the bell, and all that stuff, we can draw these lines across and we can figure out where we're at. We're going to be doing that. We're going to figure out where these things are on the Earth. We're going to do a back azimuth, and we're going to draw our lines, and we're going to figure out where we're at. This is what Noonan was doing, or at least that's what he was supposed to be doing, and I think he was, because they end up pretty much where they're supposed to be. Why they were so far south, I've already discussed what I think happened, and I will explain that a little further as we get more into this. But this is essentially celestial navigation, plotting these locations on the Earth, getting a back azimuth, and drawing your lines across to determine where you are. Now let's look at hour angle, because this is critically important. In fact, this is what makes this whole bowl of spaghetti work. What we have here is a representation of the Earth, this being the North Pole. This is GMT, Greenwich, England. Greenwich Mean Time starts here. This is the international date line. 11 hours this way, 11 hours this way, giving us a total of 24 hours. Hour 12 down here, this is all positive, this is all negative hour angles. When you're doing your navigation, there's some tricks and that kind of stuff that are done, or if you will, applications in order to get your location. But let's go back up here. The lines of longitude are every 15 degrees. Every 15 degrees is 1 hour apart. The sun passes over each one of these lines of longitude plus or minus 20 minutes of what is going to be high noon at each one of these locations. That is, if you have a stick in the ground, the shadow will be the shortest 20 minutes before or 20 minutes after the hour, and it may be that it's going to come up right on 12 o'clock that it's the shortest. But because of the movement of the Earth, that has to do with the rotation of the Earth, the orbit, just a whole lot of things, the sun can pass plus or minus 20 minutes of each one of these locations. Doesn't mean it will, just means that it can. These are called your hour angles. If you're down here and you shoot the sun, what you're doing is you're getting an hour angle from GMT, or Greenwich, based on Greenwich Mean Time, as to where the sun is on the face of the Earth. Commit this to your memory. You have to know the hour angle. That is how many hours past GMT the sun is when you do your sight, in order to be able to determine where the sun is on the face of the Earth. When you're on the other side of the international date line, it's the same thing, but it's done differently. The international date line has screwed up a whole bunch of people. The last major foul-up that I heard about was the Air Force trying to fly, I think it was F-35s, to Japan or Taiwan or something, and when they crossed the international date line, the computer had not been programmed to deal with that. They lost their navigation and they had to fly back to Hawaii because their pilots didn't know how to do basic navigation, which is a failure on the part of the Air Force. And the Air Force is not here to defend themselves, so I will point out that their pilots are real good with technology, but they're not real good if the technology fails them, which comes back to Amelia Earhart. She was using a technology, navigation, and the ship broadcasting a signal. She was relying on technology to get her there. When everything failed, she didn't have a backup plan. Again, failure of imagination. So with this done, I'm going to break this into a couple of segments, because otherwise it's going to get too long and some people might want to skip over some of this stuff and get to the juicy parts. So I will go ahead and sign off of this segment. This is part 3 of Amelia Earhart and how we lost her. Dysfunctional Vet out.